The research proposes a novel transform method for processing multidimensional graph signals, specifically focusing on the linear canonical transform domain. This method, known as the multidimensional graph linear canonical transform, M-D GLCT, is designed to efficiently process graph signals with complex topological structures. The M-D GLCT is based on the central discrete dilated Hermite function, 2D CDDHFs-GLCT, and the chirp multiplication-chirp convolution-chirp multiplication decomposition, 2D CM-CC-CM-GLCT. Theoretical analysis and simulation results demonstrate that the M-D CM-CC-CM-GLCT algorithm has a reduced computational complexity while maintaining comparable additivity and better reversibility compared to the M-D CDDHFs-GLCT. The M-D GLCT is further applied to data compression, showcasing its advantages in algorithm design and implementation. This work has significant implications for the processing of high-dimensional data in various fields, including radar surveillance, biomedicine, and image processing. In the realm of graph signal processing, the graph Fourier transform, GFT, and its variants have been pivotal in representing and analyzing graph signals. However, these transforms often disregard the product structure inherent in multidimensional graphs, leading to a lack of directional information in the signal spectrum. To address this issue, the multidimensional GFT, M-D GFT, was proposed, which rearranges the unidimensional spectrum obtained by GFT into a multidimensional frequency domain, capturing the directional frequency along each factor graph. The fractional Fourier transform, FRFT, has also been introduced into graph signal processing to enhance the extraction of local graph signal features. By incorporating a rotation angle parameter, FRFT allows signal representation in the fractional domain, situated between the time and frequency domains. However, similar to GFT, the graph FRFT, GFRFT, encounters the challenge of representing the spectrum of multidimensional graph signals, neglecting the product structure in the graph. Consequently, the multidimensional GFRFT, M-D GFRFT, was defined, avoiding the binary spectrum of unidimensional GFRFT, showing directional characteristics of multidimensional graph signals, and reducing the computational complexity of graph fractional domain. Furthermore, the linear canonical transform, LCT, has been extended to graph signals processing, offering greater flexibility and freedom compared to GFRFT. The graph LCT, GLCT, can achieve better signal representation and has been defined based on central discrete dilated Hermite function, CDDHFs-GLCT, and chirp multiplication-chirp convolution-chirp multiplication decomposition, CM-CC-CM-GLCT. While these discrete algorithms exhibit favorable properties, they are associated with high computational complexity, posing challenges for practical application. To overcome these shortcomings, this paper proposes two kinds of multidimensional graph linear canonical transform, M-D GLCT, applied to multidimensional graph signals, based on CDDHFs and CM-CC-CM decomposition respectively. The M-D GLCT rearranges the unidimensional spectrum obtained by GLCT into the multidimensional frequency domain, providing the multidimensional spectrum of signals. In addition to the frequency characteristics provided by traditional GLCT, the proposed M-D GLCT also includes directional information, showing its advantages in signal denoising, filtering, and other applications. The main contributions of this paper include the proposal of the 2D CDDHFs-GLCT and the 2D CM-CC-CM-GLCT, which are both irrelevant to the sampling periods and without oversampling operation. The extension of these transforms to multidimensional, M-D CDDHFs-GLCT and M-D CM-CC-CM-GLCT, is also defined. In terms of computational complexity, M-D CM-CC-CM-GLCT exhibits lower computational complexity than M-D CDDHFs-GLCT, making it more efficient and practical for applications. Additionally, M-D CM-CC-CM-GLCT achieves similar additivity compared to M-D CDDHFs-GLCT and has better reversibility, offering an auxiliary thinking in some applications such as coding and decoding. Finally, the M-D GLCT is employed for data compression to demonstrate its advantages. Experimental results indicate that M-D GLCT achieves closer fidelity to the original data compared to M-D GFRFT at equivalent compression ratios, with smaller errors. This research paper proposes two novel graph-based transforms, namely 2D CDDHFs-GLCT and 2D CM-CC-CM-GLCT, and extends them to M-dimensional versions. The paper begins by introducing basic 2D graph operations, including Cartesian product graphs, 2D graph Fourier transform, 2D graph Fourier transform with rotation, 2D graph convolution, and 2D graph scaling transform. A Cartesian product graph is defined as the product of two graphs, G1 and G2, with vertex set V1 times V2 and edge set E satisfying certain conditions. The adjacency matrix, degree matrix, and Laplacian matrix of the Cartesian product graph can be expressed as the Kronecker sum of the corresponding matrices of the factor graphs. The 2D graph Fourier transform is then introduced, which is defined as the Jordan decomposition of the graph shift operator Zn. For undirected real-weighted graphs, the graph Fourier transform matrix FGN is obtained, and the 1D graph Fourier transform of a signal x on a graph G is defined as O1-DGFT x equals FGNX. The 2D graph Fourier transform is extended to Cartesian product graphs, where the graph shift operator Zn is decomposed, and the 2D graph Fourier transform of a signal x on a Cartesian product graph G1 hollow square G2 is defined as x equals n array summation I1, I2 VZ1 less than I1, lambda 1, K1 greater than VZ2 less than I2, lambda 2, K2 greater than x, I1, I2. The paper outlines the structure of the remaining sections, which will define the 2D GLCT based on CDDHFs decomposition in CM-CC-CM decomposition. Extend these transforms to M-dimensional versions. Compare their computational complexity, additivity, and reversibility, and apply M-D GLCT to data compression. The paper concludes by summarizing the proposed transforms and their applications. The paper presents formulations for two-dimensional graph signal processing, including the 2D graph Fourier transform, 2D graph fractional Fourier transform, 2D graph chirp multiplication, and 2D graph scaling transform. The 2D graph Fourier transform is represented as a chain of matrix-matrix multiplications, denoted as x equals fg1x, fg2, t, where x is the input signal and fg1, fg2 are graph Fourier transform matrices. The inverse transform is represented as x equals f-1g1 xf-1 g2t. The vector formulation of the 2D graph Fourier transform is given as O2DGFT, x, equals fg2 circled times fg1, x, where x is the vectorized input signal. The 2D graph fractional Fourier transform is defined by decomposing the graph shift operators Z1, Z2 as O alpha 2D GFRFT, x, equals fg2 circled times fg1, alpha x, where alpha is the fractional Fourier transform parameter. The 2D graph fractional Fourier transform operator is denoted as O alpha 2D GFRFT. The 2D graph chirp multiplication is defined by decomposing the graph shift operators Z1, Z2 as O she 2D GCM, x, equals JF2 circled times JF1, she x, where she is the graph chirp multiplication parameter. The 2D graph chirp multiplication operator is denoted as O she 2D GCM. The 2D graph scaling transform is an extension of the shift operation to general graph signals, where the relational dependence between data is represented by arbitrary graphs. The transformation result of the graph shift is given by the product of the input signal and the relation matrix of the graph. The paper provides a comprehensive framework for two-dimensional graph signal processing, including the definitions of 2D graph Fourier transform, 2D graph fractional Fourier transform, 2D graph chirp multiplication, and 2D graph scaling transform. These formulations enable the analysis and processing of graph signals in two-dimensional spaces, which is crucial for various applications in computer vision, signal processing, and machine learning. The paper discusses the extension of graph signal processing to two-dimensional, 2D, graphs, focusing on the 2D graph linear canonical transform, 2D GLCT. It introduces the 1D graph scaling transform and its extension to 2D graphs, defining the 2D graph scaling transform. The 2D GLCT is then extended to Cartesian product graphs through 1D GLCT. The implementation algorithms for 2D CDDHFs-GLCT and 2D CM-CC-CM-GLCT are presented, based on the additivity of 2D GLCT and the decomposition of the parameter matrix. The parameter matrix of 2D GLCT is a 4x4 transform matrix, known as the ABCD matrix, which is decomposed into 3 or 5 matrices. The paper also discusses the relationships between different transforms, such as 2D GFT, 2D GFRFT, 2D graph CM, and 2D graph scaling transform, all of which are special cases of 2D GLCT. A fast algorithm for calculating 2D GLCT is proposed, based on CDDHFs decomposition. The summary highlights the technical aspects of the paper, including equations, algorithms, and mathematical concepts, providing a comprehensive overview of the research. This research paper discusses the decomposition of 2D generalized linear canonical transform, 2D GLCT, on Cartesian product graphs, which is a special case of Iwasawa decomposition of symplectic matrices. The 2D GLCT is realized by combining 2D graph continuous morphological transform, CMT, 2D graph scaling transform, and 2D generalized fractional Fourier transform, GFRFT. The 2D CDDHFs-GLCT is defined as the decomposition of graph shift operators, GSOs, on Cartesian product graphs, which can be expressed as a combination of 2D graph CMT, 2D graph scaling transform, and 2D GFRFT. The paper also introduces the 2D CM-CC-CM-GLCT, which is a decomposition of 2D GLCT without scaling operation. This decomposition is based on CM-CC-CM decomposition, where the 2D parameter matrix is expressed as a product of 3 matrices. The first matrix corresponds to 2D graph CMT with chirp rate Xi1. The second matrix corresponds to 2D graph CC with parameter B. And the last matrix corresponds to 2D graph CMT with chirp rate Xi3. The 2D graph CC can be further decomposed into a product of 3 matrices, resulting in the 2D CM-CC-CM-GLCT. The paper discusses 2 cases. DETB does not equal 0 and DETB equals 0. In the case of DETB does not equal 0, the 2D CM-CC-CM-GLCT is defined as the decomposition of GSOs on Cartesian product graphs, which can be expressed as a combination of 2D graph CMT, 2D inverse graph Fourier transform, IGFT, and 2D graph CMT. The relationship between the parameters Xi1, Xi2, Xi3, and the parameters A, B, C, D is given. In the case of DETB equals 0, 2 kinds of decomposition are considered. The 2D CM-CC-CM-GLCT is defined as the decomposition of GSOs on Cartesian product graphs, which can be expressed as a combination of 2D graph CMT, 2D IGFT, and 2D graph CMT. The relationship between the parameters Xi4, Xi5, Xi6, and the parameters A, B, C, D is given. The phase differences between FT and LCT, and IFT and LCT, are also considered. Overall, this research paper presents a comprehensive study on the decomposition of 2D GLCT on Cartesian product graphs, which has important implications for signal processing and graph signal processing. The proposed methods provide a new perspective on the decomposition of 2D GLCT and can be applied to various fields such as image processing and graph-based signal processing. Here is a combined summary of pages 13 and 14 of the research paper. The paper introduces two multidimensional graph linear canonical transform (GLCT) methods: multidimensional CDDHFs-GLCT, M-D CDDHFs-GLCT, and multidimensional CM-CC-CM-GLCT, M-D CM-CC-CM-GLCT. The M-D CDDHFs-GLCT is defined as a decomposition of graph shift operators, GSOs, on a Cartesian product graph, with parameters xi, sigma, and alpha. The relationship between these parameters and the original parameters a, b, c, and d is established through equations 33 and 35. The M-D CM-CC-CM-GLCT is also defined as a decomposition of GSOs, but with different parameters and relationships to the original parameters. Two cases are considered: when the determinant of matrix B is non-zero, definition 12, and when it is 0, definition 13. The relationships between the parameters are established through equations 37 and 40 for the non-zero case and equations 41 for the zero case. The paper then compares the M-D CDDHFs-GLCT and M-D CM-CC-CM-GLCT in terms of computational complexity, additivity, and reversibility. The 2D case is taken as an example, and the matrix form of the 2D CDDHFs-GLCT is recalled from equation 23. The computational complexity of the M-D CDDHFs-GLCT is analyzed, showing that it requires real and complex multiplications. The research paper discusses the computational complexity of two-dimensional 2D CDDHFs-GLCT and 2D CM-CC-CM-GLCT. The authors provide a detailed comparison between these two transforms in terms of their complexity, additivity, and reversibility properties. The complexity analysis reveals that the 2D CM-CC-CM-GLCT has a lower computational complexity than the 2D CDDHFs-GLCT for certain cases. The additivity property of the 2D GLCT is expressed as matrix multiplication, and the authors compare the normalized mean square error, NMSE, of the additivity property for both transforms. The results show that the 2D CM-CC-CM-GLCT has similar performance to the 2D CDDHFs-GLCT in the additivity property. Furthermore, the authors compare the reversibility of the two transforms by checking the NMSE of reversibility. The results indicate that the 2D CM-CC-CM-GLCT is more reversible than the 2D CDDHFs-GLCT. In conclusion, the paper provides a comprehensive comparison between the 2D CDDHFs-GLCT and 2D CM-CC-CM-GLCT, highlighting their differences in computational complexity, additivity, and reversibility properties. This research contributes to the development of efficient graph signal processing techniques and provides insights into the performance of various transforms under different conditions. The paper presents a comparative analysis of two-dimensional 2D graph signal processing techniques, specifically focusing on the additivity and reversibility properties. It introduces two novel methods, 2D CDDHFs-GLCT and 2D CM-CC-CM-GLCT, which are designed to improve the performance in these properties. In Figure 1, the authors showcase four different 2D graph signals, labeled as x1 to x4, each representing distinct spatial distributions. Table 2 compares the additivity running averages of these signals using both methods. The results indicate that while both methods exhibit low additivity errors, the 2D CM-CC-CM-GLCT method slightly outperforms the 2D CDDHFs-GLCT method across all signals. Figure 2 illustrates the normalized mean square errors, NMSEs, for the additivity property over 50 different sets of matrices M1 and M2. This figure highlights the robustness of the proposed methods under varying conditions. Table 3 provides a comparison of the reversibility running averages for the same signals. Here, the 2D CM-CC-CM-GLCT method significantly outperforms the 2D CDDHFs-GLCT method, demonstrating better reversibility properties. The authors emphasize the importance of these properties in graph signal processing, as they directly impact the accuracy and reliability of the processed signals. The proposed methods are designed to minimize errors and improve the overall performance in these aspects. This research contributes to the advancement of graph signal processing techniques, offering novel solutions for enhancing the additivity and reversibility properties. The research paper discusses the development of a novel framework for multidimensional graph signal processing, leveraging the graph Laplace transform, GLCT, and its variants. The authors propose the use of the 2D CDDHFs-GLCT and 2D CM-CC-CM-GLCT, which are extensions of the 1D CDDHFs-GLCT and CM-CC-CM-GLCT, respectively. These new frameworks are designed to handle signals defined on multidimensional graphs, providing an efficient way to analyze and process such signals. The authors compare the two proposed frameworks in terms of complexity, additivity, and reversibility. The results show that the 2D CM-CC-CM-GLCT has better additivity and reversibility properties compared to the 2D CDDHFs-GLCT, although it has higher computational complexity. This is demonstrated through normalized mean square errors, NMSEs, of the reversibility property for 50 different sets of M, as well as a comparison table detailing the complexity, additivity, and reversibility of both frameworks. The paper also explores the application of the M-D GLCT in data compression, comparing it with M-D GFRFT. The authors use a 2D graph signal as an example, calculating the 2D CM-CC-CM-GLCT of the signal and ranking the coefficients according to their absolute values. They then reserve the maximum amplitude coefficient of a fraction gamma, compression ratio, and set the remaining coefficients to 0. Finally, they perform 2D IGLCT on the coefficients to obtain the compressed and reconstructed signal. To measure the compression loss, the authors use three quantities: relative error, RE, normalized root mean square, NRMS, and correlation coefficient, CC. These metrics are used to evaluate the error between the compressed signal and the original signal, as well as the compression efficiency. The results indicate that the M-D GLCT provides better compression effects compared to M-D GFRFT, highlighting its potential in various signal processing domains. The authors propose a multidimensional graph signal processing method that preserves dimension information of multidimensional graphs. They introduce two-dimensional graph linear canonical transforms, namely, 2D CDDHFs-GLCT and 2D CM-CC-CM-GLCT, derived from CDDHFs decomposition and CM-CC-CM decomposition. The authors extend these transforms to multidimensional, resulting in M-D CDDHFs-GLCT and M-D CM-CC-CM-GLCT. Experiments are conducted to evaluate the performance of 2D GFRFT and 2D CM-CC-CM-GLCT under different compression ratios gamma. The optimal rotation angle alpha is selected for 2D GFRFT, where alpha equals 1, degenerating into 2D GFT. The results show that 2D CM-CC-CM-GLCT provides a better transformation basis and produces smaller errors compared to 2D GFRFT. Table 5 presents the relative error, RE, of 2D GFRFT and 2D CM-CC-CM-GLCT with different gamma. The parameters selected for 2D CM-CC-CM-GLCT are detailed in the table. Figure 4 illustrates the relative error, normalized root mean square, NRMS, and correlation coefficient, CC, of 2D GFRFT with different rotation angles alpha for different compression parameters gamma. The results indicate that the optimal rotation angle alpha is 1 under different compression ratios. Table 6 presents the NRMS of 2D GFRFT and 2D CM-CC-CM-GLCT with different gamma. The parameters selected for 2D CM-CC-CM-GLCT are detailed in the table. The results show that 2D CM-CC-CM-GLCT provides smaller NRMS compared to 2D GFRFT. The authors conclude that M-D CM-CC-CM-GLCT can effectively preserve more data details and structural information in the compression process, resulting in more accurate restoration of original data characteristics without significant distortion or errors introduced by compression. The proposed method has potential applications in graph signal processing and compression. The research paper discusses the comparison between 2D GFRFT and 2D CM-CC-CM-GLCT with different compression parameters gamma. It highlights the optimal rotation angles for both methods and their respective parameters for various gamma values. The results show that both methods have high CC values, with 2D CM-CC-CM-GLCT performing slightly better. The paper then shifts focus to M-D CM-CC-CM-GLCT, comparing it with M-D CDDHFs-GLCT. Theoretical analysis indicates a reduced computational complexity for M-D CM-CC-CM-GLCT, while simulation results demonstrate comparable additivity and better reversibility. The application of M-D GLCT to data compression is also explored, showing superior fidelity to the original data compared to M-D GFRFT at the same compression ratio. The paper concludes by referencing key works in signal processing on graphs, emphasizing the importance of these concepts in high-dimensional data analysis. Here is a combined summary of pages 25 and 26. The authors provide an extensive review of existing literature on graph signal processing, specifically focusing on graph Fourier transform, graph filters, and graph transforms. They cite various works on graph signal processing, including low-pass graph signal processing, 8, distributed nonlinear polynomial graph filters, 9, multidimensional graph Fourier transform, 10, and forecasting multidimensional processes over graphs, 11. Additionally, they reference papers on sampling theory for graph signals on product graphs, 12, fractional Fourier transform on graphs, 13, and fractional spectral graph wavelets, 14. The authors also explore the windowed fractional Fourier transform on graphs, 15, joint time vertex fractional Fourier transform, 16, and multidimensional graph fractional Fourier transform, 17. Furthermore, they discuss the sparse discrete linear canonical transform and its applications, 18. The literature review is comprehensive, covering a wide range of topics in graph signal processing, including graph transforms, filters, and signal processing techniques. The authors then shift their focus to discrete linear canonical transforms, citing works on discrete quaternion linear canonical transform, 19, applications of linear canonical transform to digital image processing, 20, and modeling circulating cavity fields using the discrete linear canonical transform, 21. They also reference papers on discrete linear canonical transform on graphs, 22, eigenfunctions of linear canonical transform, 23, and chirp multiplication by four-wave mixing for wide-band swept frequency sources, 24. Finally, the authors mention a submitted paper on graph linear canonical transform based on CM-CC-CM decomposition, 25, and a paper on topics in graph theory, specifically graphs and their Cartesian product, 26. They conclude by referencing a paper on learning product graphs from multidomain signals, 27, and a paper on fast and accurate computation of two-dimensional non-separable quadratic phase integrals, 28. The authors leverage the Iwasawa decomposition of a perplectic matrix, as explored in 29, to derive an efficient algorithm for computing the linear canonical transform, LCT. By exploiting the CM-CC-CM decomposition, they establish a fast discrete LCT, FDLCT, method, building upon the work in 30. This novel approach facilitates the decomposition of the LCT matrix into three matrices, namely, a diagonal matrix, a permutation matrix, and a circulant matrix. The FDLCT algorithm is formulated as a three-stage process. Firstly, the input signal is multiplied by the diagonal matrix, followed by a circular convolution with the permutation matrix. Finally, the output is obtained by multiplying the result with the circulant matrix. This decomposition enables the use of fast Fourier transform, FFT, algorithms, significantly reducing the computational complexity. The authors provide a detailed analysis of the proposed method, including the derivation of the FDLCT matrix and its properties. They also present a theoretical comparison with existing methods, highlighting the advantages of their approach in terms of computational efficiency and accuracy. Figure 1 illustrates the block diagram of the FDLCT algorithm, showcasing the three-stage process. The computational complexity of the proposed method is analyzed in Table 1, demonstrating a significant reduction in computational time compared to existing methods. The authors acknowledge the limitations of their approach, noting that the FDLCT method is sensitive to the choice of decomposition parameters. Future work involves exploring optimal parameter selection methods to further improve the performance of the FDLCT algorithm. Overall, this work contributes to the development of efficient and accurate LCT computation methods, with potential applications in various signal processing domains.